Okay, this is the intro to the, let's get rid of this and return to the screen share. This is an intro to experiment 22, fields and equipotentials. This should be a fairly simple um, experiment for you to do because there's no calculations. I may have a cat visiting me in a bit. There's no calculations to perform. It's just really observing. I would, if you care to try to do this experiment yourself, I'll give you some bonus points. I don't know, 10 extra points for the out of the possible 100 that you have for the experiment. You don't have to do it. It might be a little bit difficult. I don't want you getting frustrated um, trying to perform the experiment. Now I could read the intro to you, but I'm not going to. I expect you to read it yourself. But I'll highlight some points so that you definitely want to answer the advanced study assignments, the advanced study assignment, and I'm going to point out some areas here in the introduction, and in particular this area here. Oops, that's an erase. The electric force per unit charge is a vector quantity called the electric field intensity, or simply the electric field E. And you've been able to see this on the PhET simulation that I've been performing. And similarly, the magnetic force per unit pole is a vector quantity called the magnetic field intensity, or magnetic field B. Now, we haven't gotten to magnetic fields, but they lump them together in this fields and equipotentials lab, so I mentioned it also. Now, you had Coulomb's law. This is Coulomb's law here. Force is equal to K, the electrostatic, the Coulomb's constant, Q1, Q2 over R squared, where Q1 and Q2 are the charges involved. And we know that like charges repel and unlike charges attract. And these, okay, here for a single positive charge, you can see the electric field lines are emanating outward. Now this one, you can see that the lines closest to the charge are longer than the ones that are further out. In other words, the electric field diminishes as it extends out. Now these are the equipotential lines, and we're going to draw those, or the simulator is going to draw them. These are the equipotentials. Those are the areas where the potential, the voltage, I know we haven't gotten to voltage yet, where the voltage is the same for in this area surrounding the charge. And we're going to draw those equipotential lines. And here's a dipole of electric field. I think you'll certainly be able to see it in simulation. I'm about to do, but I think you may have seen it in some of the lecture notes. Here is the electric field is the force divided by the Q naught, the test charge. So it's KQ naught times Q divided by Q naught R squared. So the electric field is simply, for a single charge, it's KQ divided by R squared. That's an important one to know. Let's see, here's one. To move a positive charge from B to A would require work supplied by an external force to move the charge against the electric field force, or the electric field. The work W per charge Q naught in moving the charge between 2 points in an electric field is called the potential difference, delta V. And we're going to get to that in a future lecture. But here, delta VB to A is equal to VB minus VA, which is equal to work divided by the unit charge, or the Q naught. Um, okay, let's. The potential is constant along paths perpendicular to the field line. Such paths are called equipotentials, and that's what I showed you here. These are equipotential lines. Okay, let's. The steady state electric field lines closely resemble the static field um, that a like configuration of static charges would produce. Okay, and then here's some magnetic um, magnetic information. We'll get to magnets later. Let's read this highlighted area. A single magnetic pole or magnetic monopole has never been observed. So the magnetic field is mapped using the north pole of a magnetic pole, for example, the magnetic needle of a compass. So basically what they're saying, like if you look up here, you see we can have a single charge, just a positive charge or a negative charge. You can't have a north, just a north uh, magnet. It's always going to have an opposite south. They've never uh, found what they call a magnetic monopole. They're looking for it. I think I have a Physics Today article as late as 2016 where they're searching for magnetic monopoles, but they haven't found it yet. And my core belief is that they won't find it. You're more likely to be wrong when you say what science can't do than what it can do, but that's just my opinion. Okay, and the magnetic field is expressed as B equals a force divided by QV. We won't get into that right now. We'll get into it much later. This is an image of the magnetic field surrounding a magnet, and I hope to do that in one of the uh, experiments for this lab. We'll see if it'll work. Okay, let's see if there's anything else. This is the equipment that we use. You've got this conductive paper. Now this is what we normally use when we're not when we're doing face-to-face labs. But we're going to simulate it using the FET simulator from uh, um, University of Colorado, and I'm going to do these two configurations. That one with just two a positive charge and a negative charge. There won't be any. There won't be these lines on it, but we'll simulate it, and then we're going to do a parallel plate capacitor, and we're going to do measurements with it. So that's what we're simulating. We're not going to do the galvanometer experiment. We're going to use a voltmeter or a simulated voltmeter. So you can skip, if you're reading, you can skip this galvanometer measurement. We don't do that. We don't even do it in the face-to-face lab. And we're going to do the voltmeter measurement, and we're going to do the magnetic field. We're going to sprinkle some iron filings onto a magnet, hopefully a different magnet. And there's the laboratory report is filling in the drawings. So hopefully I can get all these. I didn't mean to show you the answers. I should have erased that, but that's okay. And then you do the questions afterwards. So that's kind of the intro to this particular lab. And we'll end the intro right here.